Okay, so we finished before the break with an assignment on probability. We covered all the little topics on probability. The homework assignment was pretty basic. Tonight, you have one more assignment on probability. So you can see if there's any problems there that you may run into trouble with, and you can ask about on Friday. Now, we do, even though we are quizzing tomorrow on probability, so I guess so much for that. Make sure you get that homework done tonight. You have a quiz tomorrow. Make sure you get it in tomorrow. So what we're going to do is start with the last chapter, chapter 12. And the homework starts tomorrow on Tuesday. Tuesday, Wednesday, and Thursday is on section 1. And so that's what we're covering in today's lecture. We won't meet on Wednesday. We won't have to meet. But then we'll meet again on Friday, in which we start section 2. And then like next week, I think we don't meet on Monday. We can talk about that on Friday. Okay, so get your notebooks out and here we go. So we're talking 12.1. Define and use sequences and series. Those are two different things, sequences and series. And what we're doing in section 1 is dealing with general sequences and series. They're of all different types. And these things can be really involved if I wanted them to be. And it takes a lot of trial and error to figure them out. But I don't want to do that. I don't want to waste your time. So we're just going to do basic ones on general sequences and series. And then when we get to section 2 and section 3, we do a specific sequence and series. The one's called arithmetic and the other's called geometric. There are formulas for those that'll help you figure them out. Those are going to be a lot easier to understand. But today we'll just take a look in general at what a sequence is and what a series is and the notation involved, and then do a few problems. So we start with what is a sequence? A sequence is a function whose domain is the set of natural numbers. And that's the set 1, 2, 3, 4, ... The outputs of that function are the terms of the sequence. So when you talk about a sequence of numbers, you're just talking about having numbers separated by commas. That's a sequence of numbers. What they really are outputs to a function. And the function determines the terms of the sequence. The outputs of the function are the terms of the sequence. The input to the function is which term it is. Is it the first term, second term, third term? And that's the domain being the natural numbers, 1, 2, 3, 4, and so on. So you insert a 1 into the function rule and you see what you get out. That's considered the first term of the sequence. So Notationally, we know a function is f of x, but that's when we deal with x being a domain of all real numbers. Here, our domain is just the natural numbers, and so we're going to be using natural numbers in the domain. And for the function, we usually use letters like A, B, and C, and we would be saying A of 1 would be the function. But the notation isn't A of 1, it's A sub 1. That's special sequence notation. So A sub 1 really means A of 1. 1 is your input. You go to your rule, put a 1 in, and you generate the number, the term, and you come with the output, and that's the term of the sequence. So if I had this sequence, 2, 5, 8, 11, then A sub 1 would be 2. A sub 2 would be 5. A sub 3 would be 8. And A sub 4 would be 11. It's your first, second, third, and fourth term. So you're putting a 1 in, getting a 2 out. Putting a 2 in, getting a 5 out. Put a 3 in, get an 8 out. Put a 4 in, get an 11 out. And so the trick is going to be, when you're given a sequence, can you find the rule? That's going to be the tougher problem. There's two types of problems you're going to have. They're going to actually give you a sequence as a rule, and you're going to generate the terms. That's easy. You just put 1, 2, 3, and so on in and see what comes out. The tougher problem is when they give you the sequence and you have to discover the rule. Can you find the function? That'll be coming up. Now, when it comes to sequences, you can have finite sequences and infinite sequences. A finite sequence in general, you have a last term. So we would say A sub 1, A sub 2, dot, 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 to the last term, A sub n. You would have n terms there. An infinite sequence, there is no last term. It goes on to infinity. So A sub 1, A sub 2, A sub 3, then we just put comma, dot, dot, dot. And you don't put anything at the end. That means it goes to infinity. We're going to be studying some infinite sequence a little bit later. Okay, so here we go. Here's the first type of problem you get with sequences. Write the first 4 terms of the sequence. So here you're given the term generator, the function, as a function of n. And you just want to write the first 4 terms. So if your A sub n is 2n plus 5, what is A sub 1? What would it be? Anybody?
7.
Yes, 2 times 1 is 2 plus 5, 7. What is A sub 2? 2 times 2, 4 plus 5,
9.
9. A sub 3, 2 times 3, 6 plus 5,
11.
11. And A sub 4, 2 times 4, 8 plus 5, 13. So this is the easy problem. You're given the function rule and you're generating the sequence by just plugging in the inputs, which are the natural numbers. Here's a function rule. This function rule, by the way, is linear. That's a linear rule. This one is exponential because your variable is in the exponent. So now I got b sub n being negative 3 to the n minus 1. So what is b sub 1? What is it?
1.
1.
1. It's negative 3 to the 0, isn't it? And that's positive 1. What is b sub 2?
3.
Negative 3 to the first. It's negative 3. What is b sub 3?
9.
Positive 9. Negative 3 squared. And what is b sub 4?
Negative 27.
Negative 27.
Negative 27.
Yep.
So you can see what happens here. You happen to have a negative base, which we didn't study with exponential functions, but you can study with sequences. It ends up giving us an alternating sequence. It alternates signs. Okay, and the last one here. So any sequence I were to give you, you should very easily be able to generate the term. C sub n is n over n plus 1. So what is C sub 1?
Mr. A, can you move your board up? Yeah, thanks.
Got it?
Yep.
So what is C sub 1?
1/2.
1/2. What is C sub 2?
1/3.
No, C
2/3.
sub 2.
2/3.
2/3. What is C sub 3?
3/4.
3/4. And C sub 4?
4/5.
4/5.
4/5. All right? So there are two types of problems. And this is the first type. Given the function, given the term generator, generate the sequence. You're just putting in the natural numbers. Now comes the tougher problem. And these could be really tough if I wanted to make them so.
That makes sense.
The rules can be really hard to figure out. Okay, it's really trial and error. But I gave you ones that hopefully we can figure out. So find the term generator. So if I were to give you 3, 6, 9, 12, what is the A sub n rule?
N plus 3.
No, not n plus 3. N plus 3, your first term would be a 4.
N plus
3n.
3n.
That
It's
makes sense.
just a multiple of 3, isn't it? 3, 6, 9, 12. Multiples of 3. 3 times n. It's a linear rule. And let me tell you, in a linear rule, if you look at the terms of the sequence, there's a common difference between the terms. Difference of 3 here between all the terms. That's when you're going to get a linear rule. We're going to study those more specifically when we get to what is called an arithmetic sequence, because that's an example of one. Okay, now let's see if we can figure this one out. 2, 5, 8, 11. Now, this could be tough. 2, 5, 8, 11. Try to figure out the rule. But let me give you a hint. This is the same type where you have a common difference of 3. And when you do have that, the rule is going to be that common difference times n. You're going to get 3n, and then you're going to say, if I have 3n, what would it take when n is a 1 in order to get the number 2? if you know you have 3n and you're going to let n equal 1 and you have to come up with the number 2, what would you do?
3n minus 1.
3n minus 1. So that, otherwise, this is pretty tough to figure out, isn't it? To try to guess what that rule would be. That'd be pretty tough to do. So here, it's one of the special ones, and here's one way to do it. There's going to be a formula we're going to use to do it in section 2. But to do it this way, you take that common difference 3, and you know it's going to be 3n, and then you let n equal 1, that would give you 3, and minus 1 would give you the 2. So it ends up being 3n minus 1. Okay, now let's look at this rule. This is not a common difference, but now you need to study the numbers. 1, 4, 9, 16, 25. What is C sub n?
N squared.
N squared.
Yup.
It's simply the squares of the n. All right, so that's what I mean. Each problem can be a little bit different, what you have to look at. Now look at this one for D sub n here. 1/3, 2/4, 3/5, 4/6. Now when you have fractions, look at your numerator and then look at your denominator. The numerators happen to be what?
N.
1, 2, 3, 4, which would be
And
n, isn't it?
Yup.
That's n. Now look at the denominator. What's the
Oh.
connection between the numerator and the denominator?
N plus 2.
Okay, the denominator's 2 more than the numerator. So again, if you were just looking at these fractions, that would be hard to figure out. But if you know to look at the numerator and denominator separately, and you're looking for that connection, now you can figure it out. It's n over n plus 2. Now, let me give you one here, which is really difficult. 2, 6, 12, 20, 30. Okay,
Could you move up your camera?
can you see it?
There we go.
And
Okay, this one, I don't know if anybody has any idea at all, but I just wanted to show you one where I wanted to show you how difficult these things could be. I mean, does anybody have any idea? This is a total different type of sequence generator. So somehow 1 goes into 2, 2 goes into 6, 3 goes into 12, 4 goes into 20, and 5 goes into 30.
N
And you
squared
have to
plus
see
n.
a connection. Somebody have it?
N squared plus n.
Okay. Or in other words, what it really is this.
Okay.
Excellent. See, sometimes somebody will see it. It's really n times n plus 1, which is n squared
nice job, Trevor.
plus n. That's excellent, seeing n squared plus n. How did you see that? That's amazing. But do you see what I mean about how tough these things can be? So these are just general sequences. There's no formula. You just have to figure them out the best you can. All right? But we're soon going to be studying sequences where there are formulas, and that's where we want to spend our time. Okay, so that's sequences. All right. Now, in your notes. Let's push it back up again. We want to do series.
Let's go.
A sequence was a function. The outputs of the function were the terms of the sequence. A series is the sum of the terms of a sequence. So when you're working with series, you again are going to be working with sequences. You're going to have to find formulas for the sequences when you're working with a series. So that's why that's going to be important, to see a sequence and know what formula generates it. You're going to need to do that for series. Now, you have finite series and you have infinite series. A finite series, 2 plus 4 plus 6 plus 8. It has a last term, and you would just add them up. An infinite series, 8 plus 4 plus 2 plus 1 plus ... goes on to infinity. And your first inkling would be to say, finite series definitely has a sum, don't they? You just add up all the terms. But can an infinite series have a sum?
No.
And the question, and the answer is certain ones can, but it involves limits. It has to be the right type for an infinite series to actually make sense that it has a sum, even though you're adding infinite number of terms. It turns out that certain ones are limited as to how big they can get, and that limit is defined to be the sum. Those we're going to study in section 4. After we do arithmetic and geometric, we're going to study infinite series. So you'll get a big kick out of those. It turns out it's easier to find the sum of an infinite series than it is a finite series. The formula is a lot simpler. But here's a finite series, 2, 4 plus 4 plus 6 plus 8. We use what is called sigma notation. This symbol is a Greek letter for S, it's sigma. The index we use usually is I. You can use N, you can use A. Usually we use I. When we say I equals 1, then the upper limit here is 4. You're saying I goes from 1 to 4, incrementing by 1. So I would be 1, 2, 3, and 4. The 2i is the term generator. That's what generates the sequence up here. 2, 4, 6, 8. Those are the terms of the sequence that we're adding. So 2i would give you 2, 4, 6, 8 as I goes from 1 to 4. So this sigma says add them up. So let I equal 1, you get a 2. Sigma says add it to I equals 2, you get a 4. Add that to I equals 3, you get a 6. Add that to I equals 4, you get an 8. And you would get 6 and 6 is 12 and 8 is 20. So sigma from 1 to 4 of 2i would equal 20. Finding the sum of a series. You actually get an answer. It adds up all the terms. But you can see the sigma notation uses a sequence generator. You need to know the formula for the sequence of the numbers you're adding. This one is a special one we're going to study later. 8421 turns out to be 8 times 1/2 to the I minus 1. When I equals 1, you get 1/2 to the 0 is 1 times 8, you get your 8. When I equals 2, 1/2 to the 2 minus 1 is 1/2 times 8, you get your 4. When I equals 3, 1/2 to the 3 minus 1 is 1/2 squared, is 1/4 times 8, you get your 2. And when I equals 4, I minus 1 would be 3, and 1/2 cubed is 1/8 times 8 is 1. And what we're doing here is an infinite series. And so we would say I goes from 1 to infinity. There is no upper limit. It's an infinite series. It has an infinity symbol. This happens to be one that does have a sum, because I know what special type it is. You're going to learn about those later. But if I gave you this, you would have to figure out the formula for 8421. And there's a special formula for that you're going to be taught to know that it's that. Right now, I just wanted to show you that. Okay, now, there are 2 types of problems you're going to have with series. In the one problem, you're given the sigma notation and you're asked to find the sum of the series. What is the sum of that series? So you generate the numbers and add them up. Later on, if it's a special series, there will be a formula for giving you the sum. You won't have to generate all the numbers and add them up. Right now, you don't know any formula. So you just have to generate the numbers and add them up. But that's simple to do, just takes a little time. That's the first type of problem. The second problem is when you're given the series like this and you have to write it using sigma notation, which means you've got to find the term generator for the sequence you're adding. And that's the tougher problem. So let's do some of these problems. What sigma I equals 1 to 5 of 8i? Well, what is that going to be? When I is 1, that's an 8. When I is 2, it's a 16. When I is 3, it's a 24. When I is 4, it's a 32. And when I is 5, it's a 40. So all you're doing is plugging in from 1 to 5. And now you add these up. 24 is 48, 32 is what, 80, and 40 is 120. But that's all you're doing, nice and simple. Plug the numbers in, generate those numbers, and add them up. Now look at this one. This time we're starting at 3 and going to 7. Again, you go up by 1. But your first term is going to be when k is 3. 3 squared is 9 minus 1 is 8. So you're starting with an 8. Plus, let k equal 4. 16 minus 1 is 15. Then let k equal 5. That's 24. Then let k equal 6. That's 35. And then let k equal 7, that's 48. And so you could put it on a calculator or just do it in your head and add those numbers up and you'd get that sum. All right, but we don't always have to start with the 1 if we don't want to. This is adding from 3 to 7. of this term generator. All right, but that's why these are easy. You're just plugging the numbers in and getting the outputs and adding up the output. Now, pay attention to this one. Sigma C equals 1 to 20 of 1. So the term generator here is the function a sub n equals 1. Not a sub n equals n, a sub n equals 1. That means every output is a 1. So when you let C equals 1, your C sub 1 is 1. When C is 2, your C sub 2 is 1. Your C sub 3 is 1. What are you doing here? You're adding up how many 1s?
20.
21. So what does it add up to?
20.
20. So this is a constant sequence generator. It's a sub n equals 1. Not a sub n equals n, but a sub n equals 1. Every output is a 1. It's a constant function. Okay? So that's a little different. Now this one is your a sub n equals the n, or a sub I equals I. Now when you go to 1 to 6, what are you getting? Well, when C equals 1, the I is 1. When C equals 2, the I is
2.
2. And then 3,
4.
4,
5.
5, and
6.
6. So you're just adding 1, 2, 3, 4, 5, and 6. In the book, you should read this in the book. There's a special formula for this problem. There's a special formula for this problem. And there's a special formula for this problem. Make sure you read them in the book. This one is I equals 1 to 4 of I squared. So this is just going to be 1 squared plus 2 squared plus 3 squared plus 4 squared. And you're going to add them up. So these are the easy problems. You just generate those numbers and you add them up. Any problems with that?
How could you start with the third term?
We can start anywhere we want.
Okay.
And we can go to anywhere we want, but these have to be natural numbers.
So it's not taking the series of the whole sequence, you're just starting
Right,
at
we were starting with the third term and adding to the seventh term,
Okay.
okay? Because we can start anywhere we want if we wanted to. We just wanted to add from the third to the seventh term. We didn't want the first term, which would have been a 0. And the second term would have been a 3. We're not using those numbers. We're starting with our first term to
Do
be
you have
when
zero
A
term?
is 3. Okay, now let's get to the tougher problem. Can we see all of that? Can we see them now?
Yes.
Okay, write using sigma notation.
Oh.
So now, 5 plus 10 plus 15 plus dot dot plus 100. So that's going to be sigma I equals, now when we do these, we're always going to start with the 1. What's the term generator that generates this sequence? 5, 10, 15 up to 100. What's the term generator for that? Anybody?
I.
What are you getting? 5 times 1, 5 times 2, 5 times 3, up to 5 times 20, right? So what is
Five
it?
I.
It's 5i. So that's what I mean. That's why these are tougher, because you have to come up with the sequence generator. It's what we did with sequences there. You got to find the formula for the sequence. And now you have to say it's I equals 1 to what number? And you look at 100 and you let 5i equal 100, I is going to be 20. And so you're going from 1 to 20 of 5i. And we just wrote it in Sigma notation. So you can see where this is a little tougher problem, because you have to come up with that term generator. Okay, let's look at this one. Sigma I equals 1. This is an infinite series. So we're going to be going to infinity. But what's the term generator? You got 6. Then you got 36, which happens to be what?
6 squared.
6
6 to the I
squared.
power.
Then you have 216, which is 6
This third.
cubed, isn't it?
Yes.
And then the 1296 is 6 to the 4th. So what's the term generator?
6
6 to
squared
the I.
times I.
6 to the I.
Yeah.
So again, you're dealing in general series here. So the formulas could be of any type. When you study a specific one, they're all the same type. And there are formulas for them, which makes it a lot easier. All right, let's look at this one. Sigma I equals 1 again to infinity. Now, 1/2, 4/5, 9/10, 16, 17. What did I tell you about fractions?
Look at the numerator and
Look
then
at the numerator. What do you see? What's the numerator?
It was up by 2.
n
No.
n
What's the
squared.
numerator?
N
Six.
squared.
Squared.
It's I
I squared.
squared, isn't it? 1, 4, 9, 16. Next one would be 25 over 26. What's the denominator? Look at it with respect to the numerator. What is it?
+1.
It's
Plus
a
one. I squared plus
plus
1.
1. It's an I squared plus 1. So again, you have to be a little clever. You got to see it's I squared over I squared plus 1. Okay? We got that one. Now this last one, I equals 1, 2. Well, it's simply 5 plus 6 plus 7 up to 12. This is one of those that's linear. It has a common difference, doesn't it? It's 1, right? So you're going to get 1 times your n, or in this case, 1 times I. And so again, you get I, and when I is 1, you need to come up with 5. So what do?
I plus 4.
I plus 4. It's simply I plus 4. And now 5 becomes your first term, which is 4 less. 12 becomes 4 less. Your which term?
8.
The 8. So you have to figure out that upper limit here. So it's sigma I equals 1 to 8 of I plus 4. All right? So we have covered one special type so far, which is going to be called arithmetic, which we're going to study in a little different way on Friday. But when you have that common difference, you can use that to get the term generator. Otherwise, it's kind of tough figuring it out. But if you know it's that special sequence where you have that common difference, it's that difference times n. And then you figure out the first term. All right?
All right.
And that is a wrap.
Pretty straightforward.
So, Sigma Bowl.
Okay, here.